Hi everyone, this is Zihui from Caltech. I'm presenting our recent work end-to-end sequential sampling and reconstruction for MR imaging. This is a joint work with my co-first author Tianwei and Dr. He Sun, Professors Adrian Dalca, Yisong and Katie Bouman. A central challenge in MRI is a slow acquisition process, which leads to high cost, patient discomfort, and reconstruction artifacts when the patient moves. The accelerated MRI mitigates this challenge by only measuring part of the case space to reduce acquisition time. We aim to recover a good reconstruction from these partial measurements. Deep learning methods have shown state-of-the-art reconstruction performance, and there has been a recent interest in designing good sampling strategies via deep learning as well. In our work, we propose a framework that integrates two novel approaches to designing a deep sampler. Instead of predetermining a sampling pattern, our method provides adaptive sampling for individual patients. How it is done? We first sample a few measurements to get a rough reconstruction. Then our learned sampler will sequentially estimate the next best measurements to take based on the previous step. Sequential sampling allows our model to leverage intermediate information for later sampling. We also take the co-design approach to jointly optimize the deep sampler and deep reconstructor through end-to-end training. In experiments, we investigated the 1D line and 2D point sampling scenarios using the FastMRI single coil knee dataset. Now I will show you some of our experiment results. First, our trained models are adaptive to different inputs. Here we show the full acquisition process and final reconstruction of our four-step model with left and right rotated knee images as inputs. The pink areas are the selected measurements. We can see from the fourth column from the left that our model is aware of the input rotation and can sample measurements accordingly. Note that our model is not trained with rotated images but still learns to adapt to rotations. Second, our method significantly outperforms the state-of-the-art non-sequential sampling baseline loop. In these plots, the x-axis is the amount of improvement in SSIM our models have over loop, and the y-axis is the number of test samples corresponding to different improvements. Our one-step models already outperform loop on more than 75% of test samples in both 1D and 2D settings. The percentage of improved samples steadily increases as the model takes more sequential steps, reaching around 97% with 4 sequential steps. These results show the significant and consistent benefit of sequential sampling. Third, we compared our method and two sequential but not co-designed methods against loop. We see that these methods are significantly worse than our method and loop. So sampler reconstructor co-design is crucial for good performance. Here are some visual examples of our method and other baselines in the 1D setting with 4 times acceleration factor. Our reconstructions are often more accurate with more detailed local structures. For example, the white areas pointed by these arrows are wiped out by other methods, but accurately reconstructed by ours. In summary, we have presented a new framework for accelerated MRI sampling. Our code has been published online. Please check out our website for more details. Thank you for your attention.